Okay, so kinematics in one dimension. Here we go. The motion of objects, baseballs, automobiles, joggers, and even the sun and moon is an obvious part of everyday life. Motion was undoubtedly the first aspect of the physical world to be thoroughly studied, and this study can be traced back to the ancient civilizations of Asia Minor. Asia Minor is your Greece, your Persia, your Egypt, Iran, that whole Middle East area kind of thing. Very early civilizations. Although the ancients acquired significant insight into motion, it was not until comparatively recently, in the 16th and 17th centuries, that our modern understanding of motion was established. Many contributed to this understanding, but as we shall soon see, two individuals stand out above the rest, and they are Galileo Galilei, kind of a weird name, mostly known by his first name, much like Cher, and Isaac Newton, mostly known by his last name, oddly enough. You'll also notice that Galileo died in 1642, and Newton was born the very same year. Kind of a bookend kind of thing. So those were the big two. Aristotle was a Greek dude. He studied motion a lot. He was completely wrong about just about everything. Okay, so as I was saying, Aristotle, smart guy, good philosopher, didn't do a lot of experiments. People just believed him for about, 1,000 years or so. Anyways, that's a rant for another day. The study of the motion of objects and the related concepts of force and energy formed the field called mechanics. Is that on your what you need to know for the test list? Yep. Mechanics is the study of the motion of objects and the related concepts of force and energy. Mechanics is customarily divided into two parts. Kinematics, which is what this unit is all about. Kinematics is the description of how objects move. And dynamics, which deals with with why objects move. Dynamics is the force, which will be our follow-up here. Kinematics is how do objects move, things like velocity and acceleration. And dynamics is the forces that cause those motions. And really, that's what people think about when they think about physics. It's really just the introduction to physics, is all it is. We start by discussing objects that move without rotating. Such motion is called translational motion, because they translate from one spot to another. I think you guys have done translations in that, haven't you? Yeah. Where you translate over a line or something like that, right? So it's just like a move without any rotation, right? So we're not going to worry about rotations. Very challenging to deal with rotations. We'll be mainly concerned with describing an object that moves along a straight line path, which we call one-dimensional or rectilinear motion. In grade 12, we'll deal with two dimensions, things that are projectiles, footballs and baseballs and stuff like that, right? You're going to be dealing with trains and things just going forward and backwards. We start you off small. Okay, speed and velocity. Now, this was on the test, I think, wasn't it? The difference? Oh. Yeah. Should have said that. It was on the outline already. Speed and velocity are words we often use interchangeably in everyday language. In physics, we make a distinction between them. For now, we discuss only speed, which refers to how far an object travels in a given time interval. If a car travels 240 kilometers in 3 hours, we say its average speed was 80. How did I get 80? 240 kilometers, the distance, divided by 3 hours, 240 divided by 3, 80. Right? And this formula you should have learned in grade 10. V bar equals d over t. Average speed is distance over time. Your handout is slightly different than mine, isn't it? Yeah. You highlight what you want. It's your notes, right? You guys got to get away from that too. Only, highlight. It's what you need to highlight. You're the student. I'm the tour guide, right? You guys take the pictures. That's a great analogy. How did I never think of that before? I am literally the tour guide, and you guys are the tourists. You take your own pictures. Why did it take me so long to figure that out? Write that down for me, Megan, would you? I want to remember that. I am the tour guide, you are the tourists. Take your own pictures. Where D stands for distance, T stands for elapsed time, and for the speed. Oh, I think I'm missing something there, right? The V is for the speed. The bar over the V is the standard symbol meaning average. Anytime there's a bar over a letter, it means average. Average. So here's an example with your clicker. How far can a cyclist travel in 4 hours if his average speed is 11.5? I will start the question now. This is a review from grade 10. If you can't do it, that's okay. We'll just have to figure out how to get you there. Answer is 46. There's probably some people that put 46.0. It's okay. Relax. 46. How do you do it? 4 times 11.5 is 46, right? You need to be able to do that. That's grade 10. Okay, let's keep going here. Okay, let's talk about reference frames. Now, this might be something that's a little bit new. Okay? Reference frames and coordinate systems. When riding in a train, you may observe a bird flying by overhead and remark that it looks as if it's moving at a speed of 20 kilometers an hour. Now, who among us hasn't sat on a train, saw a bird outside and said, you know, that bird appears to be flying at 20 kilometers an hour? Who has never done that? Odd. Very strange, you guys. You guys are weird. Okay, but do you mean it's traveling 20 kilometers an hour with respect to the train or with respect to the ground? And what does that even mean, Mr. Bennett? Every measurement must be made with respect to a frame of reference. A frame of reference is, Emily, simply the location where you're doing the measuring. Okay? It's the location where you're doing the measuring. I'm going to say it one more time, hoping people will pick up on it. The location where you're doing the measuring. Maybe I'll say it one more time. The location where the person is doing the measuring. Why am I repeating it over and over again? Did you see how I kind of emphasized it at the start? And then some people picked up on it, and then others took a while, so I repeated. Those are the cues you got to figure out. Because Professor Quackenbush is not going to repeat it 4 times. He's going to turn, he's going to emphasize it, because that's the point of emphasis. And you got to go, oh yeah, it worked right now. That's like the tourist guide saying, this is really interesting. Take a picture. When you get home, you'll wish you had a picture. It's the reference frame is the point where you're taking the measurement from. The reference frame is the point where you're taking the measurement from. Okay. For example, thank you, Lord. That's why it's important to stay with me, right? So you know where to write it down. You know where to highlight. You can't wait and say, oh, where is that? What? Huh? What? Can't do that. You got to be with me. You got to move along with the tour guide. I love this analogy. It's awesome. For example, while on a train traveling at 9 meters per second, you might notice a person walk past you toward the front of the train at a speed of, say, 2 meters per second. So I'm sitting in my chair on the train is traveling at 9 meters per second, and the person walks by me at 2 meters per second. Now, with respect to me, with respect to the train, the person is walking 2. How fast are they moving with respect to the ground? Punch in your answer. Okay. Correct answer? I'm waiting for Drayson. Correct answer is 11. It's right there. Right? It's right there. How did you get 11? The train is moving at 9, the person is moving at 2, so Colin on the ground sees the person walking at 11. What if the person is not walking past me, but walking the other way? How fast does Colin see them walking? 7. His frame of reference is different than mine. His measurement place is different than mine. Yeah. Or walking backwards on those moving sidewalks at the airport. Same idea. Okay? So, what is the frame of reference? It's the place where you're doing the measuring from. It's always important to specify the frame of reference when stating the speed. In everyday life, we usually mean with respect to the earth. If you're driving down the highway at 100 kilometers an hour, it's 100 kilometers an hour with respect to the earth. Technically, it should be on the speed limit sign. Maximum 100 kilometers an hour with respect to the Earth. Go ahead and try to use that in court. Yeah, it won't work. Yeah, but Your Honor, someone else was traveling at approximately 47,000 kilometers an hour with respect to the sun. Not going to work for you. Okay. The value of other physical quantities also depends upon the frame of reference. For example, there's no point in telling you that Riding Mountain National Park is 100 kilometers away unless I specify 100 kilometers from where. Distances are always measured in some frame of reference or from some frame of reference. Furthermore, when specifying the motion of an object, it's important to specify not only the speed, but also the direction of motion. For example, if a friend leaves Winnipeg on a jet plane that travels at a speed of 1,000 kilometers an hour, you would like to know which direction this person is going toward. Toronto, Vancouver, Ottawa, wherever. Often we can specify a direction by using the cardinal points, north, east, south, and west. By the way, that was a common mistake on that first test. People didn't measure from north or east or south or west. They measured from the other angle. And I made a note of that on your test. Please don't do that again. This is not often convenient. So in physics, we often draw a set of coordinate axes shown to represent a frame of reference. So quite often in physics, we use 0 as what we call the origin. That is our implied frame of reference, always. You should already know that positive x is to the right, negative x is to the left. You guys know this already, right? Negative y is down, positive y is up. Okay, that's what it's saying right here. Objects positioned to the right of the origin are coordinates 0 or O on the x-axis. So you usually said have an x-coordinate with positive, points to the left or negative, blah, blah, blah. You guys know all this. You can read it again if you want. In 3 dimensions, the z-axis, perpendicular, is also used. If you need to measure in 3 dimensions, it's x, left and right, y, up and down, z, forward and backward. You can't, not on a 2D piece of paper. Although most measurements are made in reference frames fixed on the Earth, it's important to recognize that reference frames other than the Earth are perfectly legitimate. For example, scientific measurements are sometimes made on moving ships, in spacecraft, and on the moon. Okay? When they first created navigation tools, they had to account for the ship rolling on the sea and all that, right? As the spacecraft is hurtling through space at high velocity, they have to account for that. It's actually fairly complicated. We just take it for granted because everyone here, are you guys all at rest right now? All just sitting there? Nope. You're all, the Earth is spinning. It's also rotating around the sun. Our entire galaxy is rotating. You're moving faster than you realize. You just don't know it.